All right. Thank you very much, Dennis, for that amazing introduction. At the very outset, I'd like to thank Yatan for helping me manage these slides. It was a bit of challenge to convert that from, I didn't have PowerPoint on my laptop, so he actually helped me put these slides together. So thanks, Yatan. We're here to talk about IEEE 1801, and I'm going to talk about it in the context of SoC design and verification. In a typical SoC, we have, hard IPs, we have soft IPs, and when you say hard IPs, we're talking about pre-implemented designs. These could be analog mixed signal, or these could be digital hard IPs. And we also have soft IPs, and our definition is that's delivered as HDL, a synthesizable HDL. We have IOs, or special cells, and we have the general top level that does not really contain any of these IPs. The problem with SoCs is when it comes to power and power delivery is it has several different power supplies. You could have digital supplies. These could be constant supplies, variable supplies, switchable supplies, always on, type of noisy supplies. They're analog supplies. These are typically clean supplies and typically constant. You have I/O supplies, again, typically constant, used to power your I/Os. And the sources of these supplies are also different. They could come from off-chip, they could be on-chip. You could have switching regulators or LDOs generating these supplies, or you could have power switches or on-chip switchers generating these. So how do we model this? How do we, capture all this information? On top of that, we also have dynamic power states. How do these change power states? How do these turn on and off? What type of active modes there are? Is it clock gated? Is it running fast? Is it slow? Are we in a state of retention? Is the logic supposed to be retained when it's turned off? Is the memory in retention? What type of idle modes there are? In order to model all these effects through the standard 1801, or UPF as it used to be previously called, I just have to point out that 1801 also incorporates several features of CPF 2.0, which was officially also incorporated into the 1801 standard now. The idea is, in order to capture all this different power information, we end up having a lot of different power domains in our design. And there are also different power state tables that are really exhaustive. It's impossible to actually capture all the different system-level power states of a big SoC. And there are different types of strategies like isolation, level shifters, retention, power gating, repeaters that have to be captured in this power intent file. The other aspect to consider is SoCs typically operate in multi-vendor environment. You might be using a simulation engine from a particular tool vendor, and your synthesis engine might be completely different, and your backend tools and your validation tools, your emulation platforms could all be from different tool vendors. So there's a huge need for us to make sure that this power intent is consistent between them, and the features, the modeling of power, the understanding of power stays consistent between the different tools, so that both design and implementation are in sync. The other aspect of power, and this is one of the things we find very intrusive about power, is that it touches every aspect of your design. Whether you're doing power exploration, you're doing architecture, you're doing design, RTL design, emulation, simulation, power analysis, synthesis, DFT, static checks, all tools are affected by how you capture these power information. So we absolutely need to ensure that there's a consistent way we hand off this information from one tool to another, one phase to another, and we make sure it's consistent and correct across design phases. So, to sum it up, what are the different SoC low power challenges? The first category, and there are three different categories as I see it. The first category is what is it you want to do? How do you want to save power, and how do you make those design trade-offs? So the real idea here is we want to save power, but we want to keep the area impact minimal. We want to deliver the highest possible performance, and it's got to have no schedule impact. You cannot basically take extra time, which means you cannot introduce too many bugs. There must be quality control. So all that gets incorporated into schedule. So you've got to deliver the lowest possible power, highest possible power reduction with all these features. It's about making the right trade-offs. The next problem is, okay, I know I need to make these power optimizations. How do I go about it? So you've got to start off with power estimation, figuring out where you're losing the power and where you need to, kind of budget it, and how do you solve it. And you have these problems like silicon variation, and it's not just silicon. You have voltage, temperature variations, effects that you have to take into account. And we build these models. Okay, my IP is going to behave like this with respect to power. But that model does not really correlate well with silicon data. And so how do you model it? How do you make sure that this model actually grows as you have more and more information about your silicon? And also the bigger problem is dynamic power is a big function of your use cases. On a typical cell phone, we have these standard check marks. What is your power when you're in off mode? And that's the mode when your phone's idle doing nothing. And then you have like 3G voice, you have MP3 decode, you have video decode, and we have these different use cases. And our goal is to deliver a certain power for a given use case. The question is, do you have the vectors? Do you actually have the use cases ready before you can, optimize for those use cases? And in most of the cases, we typically don't have the use cases ready when we're ready to make this architectural, exploration. So that's a big problem. And, how do we somehow capture, the effect of this activity in an abstract way without having the actual information? So that's a new challenge. And the third aspect of it is how to make this flow work, how to make this whole power-aware flow work. And the first step is to actually make all design phases, cognizant of the issues of power. In the past, I've just noticed that there were several tools that were not power-aware. DFT tools were not power-aware for a long time because they didn't have to care. Why do I have to care about power? And so, having a standard actually helps tools realize the importance of, having the tools for modeling it and then using it to drive further innovation. The second thing is not just having the awareness within the tools, it's also being able to capture this intent accurately. And once you have this intent captured, you want to make sure it's implemented correctly across tools. And the bigger problem is this is all fine here in the hardware domain. How do you talk to the software guys about power? How do they validate that all the stuff that you've done is done right, and how can they actually make use of it? So, verifying power intent with, firmware or software drivers is another challenge for SoCs, and to make sure that this power intent is consistent between tools. So, this is kind of the challenges we face in an SoC space. So the next question is, okay, fine, we know these challenges. How do you think IEEE 1801 standard can help in that front? So the first advantage we see is it first of all enables us to capture this power intent. That's the biggest advantage. You can model your system. You can find out how do you partition domains. How can you model the power delivery network? And it also enables us to do early implementation planning. How should you, make your floor plans? What type of memories to choose? And how many supplies there are? How can I make that power connectivity? So it enables you to also start thinking about implementation consequences. And of course, the biggest advantage is by modeling power abstractly upfront, we could actually do RTL simulation and capture all the effects of corruption, retention upfront, at RTL stage. And actually, there's an effort to actually move this level abstraction up to almost System C now. I think Vajan's going to talk about that. The ability to actually go one level abstraction up. But at this point of time, we're talking about HDL and how can we capture power intent at HDL level. The other advantage is the way the standard is set up, it allows you to successively refine your design. As and when more information is available to you, you start augmenting it. So I don't have to capture all the effects of implementation upfront. I could do this, in an incremental fashion. I don't have to worry about my HDL configuration or parameters. Again, I could successfully refine my power intent format as and when that design information becomes available. For large SoCs, hierarchical modeling is absolutely essential. When you have your design that's so huge, you have to divide and conquer. So you have these different IPs, soft IPs, hard IPs, macros that you have to model, separately, and then hierarchically compose them at the top level. And we have features like power models that enables us to model these IPs. And above all, abstraction, how to think about power in an abstract sense without having to go into the details of supply ports or supply net connectivities, thinking about simulation power states, and just being able to compose your power intent in a simplified way using different commands. And we're going to talk about a few of these commands when we take a real design example of an SoC UPF. And that allows us to capture the power intent. On the verification side, we want to look at dynamic behavior of power. It's not just the static structural architecture of the power distribution, but how that affects your system power states. And there are different commands that help us capture that information. We also have command options to indicate the completeness of our power state table. You can talk about illegal states. You can talk about illegal transitions. So these are all features that allow us to verify the power intent in a more robust way. So now I'm going to give you an example of what a kind of a realistic SoC 1801 file looks like. There are a few commands here, but in general, what we have is a command called load UPF. And this command helps us to kind of source or load a hierarchical piece of UPF. In this case, I have a UPF file called core.upf, and there's, it resides in a certain disk, and you load it and you define the scope, which is like the HTL hierarchy to which that UPF applies to. You had maybe a UPF for I/O pads, and the IOs have their own UPF, and you could load the UPF for that. You could put conditional constructs. So UPF is tickle, so all the tickle constructs, valid tickle constructs, can also be used in the UPF. So you could use source, you could use if conditionals, you could use for each loops in your UPF file. So in this case, we've shown an example of how you could use a conditional construct, an if construct, to suppress or load a certain UPF file. The main command here is, of course, the create power domain, which refers to the creation of an abstract creation of elements that have similar power properties. So I have created a top-level power domain called PD top, and one way to reduce your file size and prevent clutter is to modularize it and kind of source different files. So what you notice in this particular file, instead of having a very lengthy SoC UPF file, you've broken the elements of the file into different subcomponents, and you could source that. So that's a tickle source command. You could source different files, and that makes your file a lot more readable. So modeling the supplies, this is one of the bigger challenges of an SoC. When you have so many different supplies, how do you kind of model the different supplies? How do you model the power states, and how do you model the system-level power transitions? So one way to look at it is to compose it into different categories. So typically, you have these I/O supplies, and we have like 1.8 volt I/O supplies or 3.3 volt USB type supplies. You list them in a table first. You start off listing all your different types of supplies. And what I also find useful to picture is to categorize the type of supply, whether that supply is a constant, whether it's a switchable supply, or it's a variable supply. And the difference between switchable, of course, is that you can turn off. You can turn off either with on-chip power switches or external switchers. With variable supplies, which is common in mobile SoCs, we do a lot of DVFS, which is dynamic voltage frequency scaling. We kind of vary voltage with frequency to reduce power. So if you don't need too much performance, you actually lower the voltage, and you also lower the frequency, so that you just get power savings for the particular mode you're in. So we have supplies that actually go through lots of different voltages, and it's good to capture that in a table to understand what are the different voltage sources and how they vary. And so in this case, what you could see is we have like 4 different voltage supplies, independent voltage supplies, and there are different types in it. The first one, the VAR1 supply is both variable and switchable, which means that you can actually turn it off completely. Whereas the third variable supply has just 2 modes, and it cannot be turned off. So you first basically build a table which lists all the different supplies. You talk about the different voltage conditions and off mode conditions. Um, this slide is showing how this table gets translated into UPF language or 1801 language. So what we've done is for each row of the previous table, we define an add power state command. And what you notice is there's a dash supply to it. So the add power state command allows us to describe the properties of either a supply or a power domain. So at this point, we listed all these different power supplies. We're going to talk about the properties of the power supplies. So you could define a supply set for each power supply in your design or each category of power supply in your design. And you define these different properties of the supply. So in this case, the first supply was considered to be on when the voltage is either 0.8 volts or 0.9 volts. You define different states for it. A nominal could mean 0.8, a turbo could mean 0.9, and off is when it's off. You can also notice there's a dash sim state. That basically tells the simulator when to consider a particular state as corrupt state. So it says dash sim state corrupt. So in this particular example, if I were to turn off this voltage supply, if it enters the off mode state, that tells the simulator to go and inject X's into your design. And so when you actually pull up your simulator and you look at your design, you can see X's coming out of it. That is to model the effect of power actually being shut off to that block. So that's what you can do. And there are different sim state options that you could use, but corrupt is one of the most popular ones, which is corrupt when you enter this particular state. So that was for each supply in your design. We kind of wrote these add power state commands, and we defined how we could define the properties of the supply itself. The next step is once you have all these supply properties modeled, you want to talk about a system level or top level power states. How do you go about doing that? So again, it's easier for us to start imagining it in the form of a table. That's what we write it. You start with a table, and you define on the first column, you define the different system level power states. I've just given norm, state 1, state 2, state 3, but you could say 3G idle or MP3 playback, and your columns could be different supplies, and they could also be different domains. Like your processor core is at this state, and your graphics is in this state, and your modem's in that state. You could build it up that way, but this is just showing a much lower level in terms of supplies. But those columns could be your subsystem states or your IP block states, and you kind of hierarchically compose your power states as well. So the idea is you start off with something that looks like that. It looks pretty complex. Oh my goodness. There's so many different combinations, so many different permutations. So the first way we try to simplify it is to come up with a table that looks like the one below. The idea is when you take all these combinations, maybe the next table is a little simpler. So the way we have K-maps, the Carnot maps, you have logic combinations, and then you kind of reduce it to something that's more easy to model. So you have these different states, and you eliminated a bunch of rows by putting don't cares or logical expressions to model what that state is. And if you have constant columns, that the state of that particular supply does not change on your system level power state. And once you have this reduced logical table which models your system state based upon the individual power states, you can then go ahead and create a command or a few lines of UPF which describe what your top level power state is in terms of the logic expressions of your individual supply states. So this is one way of modeling your system level power state. But again, as I mentioned, the columns could, in this case, these were supply states. You could actually model subsystem states, and that makes it much easier for us to build the system level power state. So this kind of gives us a more like a static view of what the system level power state is. Okay, these are my states, and we also have trigger expressions for the state. You could put a trigger expression for the state. But what's more useful in the verification construct is what are the transitions that I should actually check for? There are lots of transitional states that we don't want to account for. And to that effect, we have these describe state transition command, and that helps us to only model the useful transitions and kind of ignore the illegal ones. And this is very particularly useful when we want to do coverage analysis. If you just look at all the different states, there could be all different combinations from state 1 and state 2. But by using the state transition, we kind of build an FSM which says, oh, these are my states and these are my transitions. So in this example, what we can see is a transition from all on to all off. For instance, is an illegal transition. You couldn't make that transition. And that way you kind of eliminate illegal transitions or unwanted transitions. And that reduces your the scope that you have to verify. If you have to verify the whole thing, it's as the number of states increases, your verification scope basically exponentially grows. So you kind of limit unwanted or illegal transitions by using the keyword illegal in your described state transition. And then you also want to model all the useful transitions that you want to verify. And so what we've done is by using a combination of add power state, which models in a way as a static view of your design, and by using a described state transition, which models a dynamic view of the transitions, we can model the power states as like a proper FSM, and then use all different tools to do various static checks or dynamic simulation checks on an SoC. So to sum it up, we basically saw. Okay, sorry, there's an animation there. We basically looked at the different SoC challenges, which was how to save power, how to model power, and how to make sure the power is correctly modeled across different tools. So the biggest challenge for us is first of all we have we have need to reduce power at various use cases, and standard like 1801 enables SoC designers to address several of those using the constructs that we have seen. But a very important aspect to that is to ensure that there's tool interoperability, because power is intrusive. It affects every phase of design. It affects every aspect of design, and we want to make sure that tools behave in a consistent fashion, and this is critical to guaranteeing SoC schedules. So that was the final conclusion. So at this point, are there any questions people might have on 1801 or how 1801 can be used on SoCs, low power challenges? Okay. Thank you very much.